Astronomers go to the darkest places on Earth to see faint light from deep space. They also move away from radio-noisy humans to listen to quiet radio signals. However, there is no location on Earth or in orbit that allows them to detect the faint radio hum from before stars existed. To overcome this limitation, scientists propose building a giant radio telescope on the far side of the Moon. The Moon's lack of atmosphere and stable surface make it an ideal spot. The Lunar Crater Radio Telescope, if constructed, would be one of the largest telescopes ever built and would enable scientists to see further into the past than any existing telescope. In 2020, it received $500,000 in funding from NASA to explore its feasibility. The Earth's atmosphere is a challenge for observing various types of light, which is why telescopes are placed in space. However, radio astronomy has mainly relied on ground-based telescopes due to the atmosphere's transparency to radio waves. Nevertheless, long-wavelength radio light is blocked by the ionosphere, making space appear dark from the surface. This limits our ability to explore a significant portion of the electromagnetic spectrum for astronomical purposes. The Lunar Crater Radio Telescope will allow us to explore the universe in new ways. This telescope would fill a gap in the electromagnetic spectrum, corresponding to a cosmic epoch that we have never observed before. The oldest light we can detect is the cosmic microwave background radiation emitted when the universe was around 370,000 years old. However, there is a huge gap in our knowledge between the cosmic microwave background and the time when star formation took off, known as the cosmic dark ages. During this time, matter began to collapse and form the first stars and galaxies. By placing a giant radio telescope on the Moon, we could peer into this time and potentially observe the faint radio signals emitted by the hydrogen and helium gas that would later form stars. The radio waves emitted during the cosmic dark ages would be redshifted due to the expansion of the universe, making them difficult to detect from Earth's surface. A large telescope is necessary to capture these signals, and the Moon's stable surface provides an ideal location for such a telescope. The reflecting surface of a radio telescope can be a simple mesh of conducting material, and the telescope would need to have a paraboloid shape to focus incoming waves. By building a significant telescope on the Moon, we can overcome the challenges of observing this unexplored epoch in the history of the universe. Our largest fixed-dish radio telescopes, such as China's FAST and Puerto Rico's Arecibo, were built in valleys and had feet antennas that could slide around to different focal points. The Lunar Crater Radio Telescope, LCRT, is a proposed telescope on the Moon that will be larger than Arecibo but smaller than FAST, with a diameter of 350 meters. Building a fixed-dish telescope on the Moon has been a long-standing idea, but previous proposals were limited by the difficulty of transporting heavy support structures to maintain the telescope's shape. However, the LCRT has a unique design using a parabolic mesh that can hang like a hammock with no additional supports. This design is not only structurally sound, but can also withstand the temperature fluctuations on the Moon. The current plan for the LCRT involves landing a spacecraft with the folded-up telescope in the center of a selected crater on the Moon's far side. Harpoons are then fired to secure the telescope, and the mesh is unfolded and adjusted to form a paraboloid shape. Selecting the right crater is crucial, as the telescope will sweep out a ring as the Moon rotates. Positioning it around 15 degrees north of the equator helps avoid interference from the Milky Way and provides a clearer view of the early universe. Additionally, the chosen crater should be boulder-free and relatively deep. The current top candidate for the Lunar Crater Radio Telescope is a crater that is 1.3 kilometers across and nearly 300 meters deep. Although it doesn't have a name, it is large enough to accommodate the proposed telescope. Communication with the observatory is challenging due to the Moon acting as a shield against human radio interference. A dedicated relay satellite, potentially orbiting the Moon or parked at the Earth-Moon L2 Lagrange point, may be necessary to transmit data back to Earth. While the proposal for the Lunar Crater Radio Telescope is plausible, there are other options for studying the cosmic dark ages, such as using dipole arrays on the Moon's far side or a swarm of satellites in orbit. NASA has yet to decide the best approach for exploring this era of the universe. Support for the show can be provided through Patreon or the merch store. Now, on to comment responses for the last two episodes on dark stars and spacetime foam. One question raised is whether dark matter would diminish over an extended period due to annihilation. The answer is yes, it would diminish, but the consequences of this reduction are yet to be fully understood. If dark matter diminishes in galaxies, it could eventually cause galaxies to fall apart due to the weakening gravitational field. However, this would only happen in the distant future due to the extremely low interaction rate of dark matter particles. John Mitchell, who first conceived of black holes, called them dark stars, but his understanding predates knowledge of warped spacetime. The graphic of a black hole shown in the episode is not Mitchell's illustration, but was created for entertainment. The slowing of light and the redshifting of light yield the same size estimation for an event horizon. And if light slows in gravitational fields, then it should indeed also be deflected by them, in the same way that light is deflected as it enters a medium light water where its speed changes. So in principle, Mitchell could have guessed that dark stars might look like the interstellar black hole if he added an accretion disk. However, there's no evidence that he did so. Moving on to spacetime foam. Kellen Senna asks, if the quantum vacuum is fluctuating, is this something that could be used to perform work? Sadly not. Although a fluctuation could in principle push, say, a tiny piston in a particular direction to drive a tiny engine, the random nature of the fluctuations means you can't know which way that push will happen. And even if it happens to be in the right direction, there'll soon be another that pushes in the wrong direction. It's the same issue with using the random motion of particles of air to extract energy. If you want the whole story, check our Reversing Entropy with Maxwell's Demon episode. Gilmartin's 90 has a question regarding the statement that photons in our Heisenberg microscope warp the fabric of spacetime, noting that we typically think of only matter as doing that. It's true that an individual photon moving in a single direction doesn't warp spacetime in the same way that a particle with mass does. However, if you trap massless photons in a massless mirrored box, then the system has an effective mass which does warp spacetime. In the Heisenberg microscope thought experiment, the photon has to bounce off the object to be measured and back to the observer. Just like the mirrored box, there's a warping of spacetime between the observer and the object, although it's not quite the same type of warping as you get with mass or with a box of photons moving in all directions. Flavorful Nuggets 1 has a story to tell. I was walking to class one day when I was in college and Matt was walking out of my school in the opposite direction. I wanted to ask him so many questions, but the second I saw him, he took the hugest bite of a pastry, so I just gave him the double finger guns and said, I know you." Thankfully, he gave me the double fingers guns back, or I would have killed myself that day. Flavorful Nuggets 1, thanks for the what's up. I remember exactly where this happened, and so I know it might happen again. Next time say hi no matter what I'm stuffing into my face.